And now, coming to you live from the SkyTrain station in Metrotown, Pre-Calculus Math 11. Dance. 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 Today, Chapter 9, Linear and Quadratic Inequalities, Section 9.1, Linear Inequalities in two variables. Well, once upon a time long ago, you learned about plotting points on a number line. For instance, you would have had something like plot x is equal to 3. And then you would have drawn the number line and you would have marked it off with a few handy reference numbers so that you could see where all the numbers fit, and you would go ahead and mark 3 to correctly do this. And then your teacher got sneaky and asked you to plot points like x is equal to 1.7 or 2.1 or negative 2.4. And this helped to see how good your understanding was of the space between the integers. And some of you got it on the first time around, and maybe some of you still struggle with that awkwardly. And then you started to do some inequalities, looking at which numbers satisfy statements like x is greater than 3. Or perhaps x is less than or equal to negative 2. And so we would go over to the number line with these and draw them on there. And at this time we realized that we needed a way to demonstrate the difference between saying greater than as opposed to greater than or equal to. And the notation that we've all agreed upon is to have a shaded in circle represent equal to, so in this case x is less than or equal to negative 2 is all of the numbers over this way on the number line. And x is greater than but not equal to 3, we've left that with an open circle to indicate that it's all of the values up to but not including 3 itself. Now I know that some of you have had teachers and tutors that have asked you to draw your inequalities up above the number line, something like this or like this. I will grudgingly accept this notation even though I don't like it. My preference is that you show the range of numbers directly on the number line like I've done here in these two examples for you. Moving on, we arrived last year in Math 10 where we were graphing equations in two variables. And of course with two variables comes a graph in two dimensions, the xy plane or the Cartesian plane. And we had things like graph y is equal to 2x plus 3, which is fairly easy to graph. We're talking about all of the points xy that satisfy this equation. This is of course a linear equation with a slope of 2 and a y-intercept of 3. So we just come over here like this and go 1, 2, 3, get that y-intercept there, and then we use our slope of 2, which means we're going up 2 for every 1 to the right, or it could be down 2 for every 1 to the left, and we connect those dots with a line and we draw that graph. Well, now we want to take that equation and change the equals sign to an inequality. Now the solution to the inequality is all of the points xy such that y is always greater than, but never equal to, 2x plus 3. For instance, the point 0, 20 is a solution to this because of course 20 is greater than 2 times 0 plus 3, right? 20 is greater than 3. It's true. This does solve that inequality, but it's not the only solution. It's just one of many points that satisfy the inequality. To demonstrate the solution, the best way is to graph the inequality. And what we do here is what we just did previously. We start off by graphing that equation, y equals 2x plus 3. So again, getting my y-intercept at 3 and other points up to 1 to the right, or again down 2 and 1 to the left. Before I draw my line here, I want to just be careful. This inequality says y is greater than, but it does not say equal to. We drew the line before for y is equal to 2x plus 3. So just like we had shaded circles and open circles for one variable inequalities, we need a way to indicate the difference between greater than and greater than or equal to. And the way we do that is by using a dotted line when we're simply talking about greater than or lesser than, and a solid line when we're talking about greater than or equal to. Equal to gives a solid line. So here we are like this. The solution to this inequality will be one side of this dotted line or the other. It's almost like we're talking about two countries here. One country that's above the line, one country that's below the line, and the line itself is like the international boundary. We want in this case where y is greater than 2x plus 3. So where are those values? Well, they are right where you would expect them to be. Greater than, above the line. Everything up here has a y value that is greater than the y value calculated by 2x plus 3. And we demonstrated that before with the point 0, 20. The point 0, 20 is way up here somewhere. When we put those values into the inequality, they satisfied it. This was an example of a test point to determine which side of the line needs to be shaded. What you do is you pick a point that is not on the line and you test it in the original inequality. To be honest, usually I will use 0, 0 and not 0, 20. 0, 0 is quite easy to use. We just substitute that in like we had before. 0 greater than 2 times 0 plus 3. This gives us 0 is greater than 3. That's not true. Therefore, 0, 0 must not be part of the solution region. The solution must be on the opposite side of this line. And as we said, when we tested 0, 20, it satisfied the inequality. So a point will either satisfy it or not satisfy it, and we shade accordingly. Let's do another example. Let's graph the linear inequality for 4x minus 3y is less than negative 12. Well, we'll start by putting this into slope-intercept form, and again, before we draw the line, we'll decide whether it should be solid or dotted. Now, I've written this in a bit of a reverse order here, but don't be fooled. The b value is still 4 for the y-intercept. 1, 2, 3, 4. And the slope here is 4 over 3, which means it's going up 4 for every 3 to the right. Or I could also go down 4 for every 1, 2, 3 to the left. Before I draw it, check the original inequality. It was just less than, so this will be a dotted line running through those 2 points, or a broken line. Now, we'll take a test point and test it in the original inequality. Let's use 0, 0. Testing that in the original inequality gives me 4 times 0 minus 3 times 0 less than negative 12. Is 0 less than negative 12? No, 0 is not less than negative 12. 0 is greater than negative 12. So 0, 0 is not on the correct side. The shading in this case, again, must be above the line. And we could go ahead and choose a point that's clearly in this shaded region, something up here like negative 5, 7. That's clearly in there. You can't even see that point. Negative 5, 7. We could test that, but there's no need to. We've already tested 0, 0. It failed, and so we know that the shading must be on the opposite side. Now let's go in a different direction with this question. Let's determine an inequality that describes the graph that you see here. Well, as we can see, this graph has a y-intercept of 2 and an x-intercept of negative 5. So if we count the slope between those points, this line is going up 2 units while it goes 5 to the right. This means the slope is 2 over 5. And the equation of the line must be y equals 2 over 5x plus 2. The shading is all below this line. So these are y values that are less than the given line. but the line is also solid and not dotted, so we're less than or equal to the given line. And now it's time for
Two for You.
Number 1, graph this inequality. Ooh, that looks nasty. Look at all those fractions in there. If only there was a way to get rid of all the fractions. If only. If only. Question number 2, James burns 500 calories per hour when he is jogging and 300 calories per hour when he is walking. He wants to do a combination of the two to burn at least 3,000 calories per week. Draw a graph that shows the possibilities for the number of hours he could spend doing each activity to meet his goal of burning at least 3,000 calories. Well, that's all for today. I really did intend to keep this to less than or maybe equal to 12 minutes. So, until next time, keep your pencil sharp, and I'll see you in class.